All right, we're going to talk about inverses here, inverses of relations, inverses of functions. Essentially what we're talking about here when we talk about inverses is operations or functions that undo each other. Think about your calculator and the buttons that you have on it that you use all the time. Let's say you start with a number like 10 and you do something like add 3 to it. You have to think about what operation undoes that adding 3. Now obviously it's subtracting 3, right? Those two things are inverses of each other, inverse operations. Or if you take a number like 10 and you multiply it by 5, think about what operation undoes that. Obviously divided by 5. If you take your answer and divide it by 5, okay, you're going to get back your original number. All right, now that's what we're talking about here when we talk about inverses. We're going to talk about inverse functions, which may or may not involve more than one operation, more than one change to a number. This function right here that is f of x is 2x minus 3. There's a couple things done to x in this function. It says take a value, x, multiply it by 2, and then subtract 3. All right, so you take your value, you times it by 2, and then you subtract 3. That's what this function does. That's what f does. Okay, I'm going to write it like this. F, that's a pretty terrible looking box. Let's try again. Not much better, but f is this function that says take whatever number you give me, multiply by 2, subtract 3. Now you can fill in a table of values. Try it a few times here. For instance, if you tried, let's start in the middle and try some positive, and we'll try 0 first since it's the easiest one, and then try some positive numbers, and then we'll try some negative numbers. So our function again was f of x said take x times it by 2 minus 3. So you try those numbers. 0 is going to give you 2 times 0, right? Minus 3 is going to give you minus 3. 2 times 1 minus 3 is going to give you negative 1. 2 times 2 minus 3, and so on. You get the idea here, right? This is going to give us 3. And if you continue the pattern down here, you're going to get negative 5, negative 7, negative 9. Now we want to know what function undoes that. What function turns that around? This function f takes this value, say negative 3, and it turns it into that value. Right? When you put a negative 3 in there, what you get out is a negative 9. Now we want to know now what function is going to take a negative 9 and spit out a negative 3. So we want it to do this. When we put a negative 9 in here, we want to get a negative 3. We want to undo these two things. Now think about how you undo these. If what we did is we multiplied by 2 and then we subtracted 3, what we have to do to undo that is we have to take our x value, we have to add 3, right? Because that's the opposite of subtracting 3. And then we have to divide by 2 because that's the opposite of multiplying by 2. This function here is going to be what's called the inverse. This is going to undo it. Let's just confirm that if we start with these values, we'll get those original values back. If you put your negative 9 in there, let's see what we get. Right, I'll write it over here. Negative 9 plus 3 divided by 2. So all I did is substitute it in there. What do you get? Negative 9 plus 3, negative 6. Negative 6 divided by 2, negative 3. So it gives us what we want, right? It undoes that. It turns it back into what we started with. If you follow it along here, same thing. If you start with negative 7 here, negative 7 this time, plus 3, gives you negative 4 there, gives you your negative 2. And I think you'll find if you do the same thing with all these other ones, negative 5 plus 3 gives you negative 2 divided by 2. Negative 5 gives you negative 1. And so on here. Negative 3 Negative 3 plus 3 is 0. If you continue down here, you're going to get the same thing. Negative 1 is going to give you 1. 1 is going to give you 2. 3 is going to give you 3. All right? Now here you have two functions that are what are called inverses of each other. The first function was f of x is 2x minus 3. The inverse function was x plus 3 divided by 2. Those opposite operations. You can give a name to it, and to show the connection between the two, if this one is called f of x, this one can be called, with words you can call it f inverse of x. Now with symbols, there's sort of some unfortunate symbols that people use for inverse functions. Somebody at some point decided that a good symbol would be, instead of just saying f of x, let's move this over and put a little negative 1 in here, and for some reason they thought negative 1 would indicate inverse. Now that's liable to confuse you because you think that negative 1 is actually an exponent, and to the power of negative 1 is the reciprocal. It doesn't mean the reciprocal of f of x. It's not 1 over 2x minus 3. That's not the inverse. This is the inverse is because it undoes what f does. All right? From an equation, if you have those opposite operations, that's how you have the inverse. That's how you find the inverse. In a table here, all you need to do to find the inverse is just going to have the coordinates reversed, right? Those coordinates are reversed. All of these coordinates are reversed in the inverse here. All right? Now, if we want to find these two things easily here, let's see how these things are related to each other here. Let's write them again down here. We have f of x was 2x minus 3, and we had f inverse of x was x plus 3 divided by 2. Now if we write them both with a y instead of their function name, we're going to be able to see how they're related to each other. Because if I take one of them, say this one, and do something that you might think of from looking at the points up above, all that's happened is the x and y have switched places, right? This 3 is over there, this negative 9 is over there. They've switched places. We can do that same thing in the equation. If we want the inverse of this function of f of x, whoa, a little fast on that. If we want the inverse of this function, we can just take these two variables and switch them around. So I'm going to rewrite it. I'm going to switch them. Just like the coordinates of the points got switched, you can just trade the variables. Because when you do that then, if we now solve for y, we're going to get this function over here. And I'll show you right now. If you want to solve this, some of you probably think about it as, if you're trying to isolate this this y here, some of you think about it as, if I was to move that 3 over to the other side of the equal sign, it happens to be its inverse. Some of you think of it as, well, I have to add 3 to both sides, and then this cancels. Whichever way you think about it, you're going to end up with x plus 3 equals 2y. And then once you've done that, to get that y by itself, you got to deal with that 2. Some of you might think, well, I got to divide both sides by 2 because then that cancels. That's a good way of thinking about it, because what you end up with there is y equals x plus 3 over 2, which is what we had over here. All right? Now you might just kind of figure out for yourself that just the way that this minus 3 on one side turns into its inverse operation on the other side, if you have one operation on one side of an equation, you can write an equivalent equation with the inverse operation on the other side. It's the same with this 2. You got this whole side multiplied by 2. You can write it equivalently with the whole side divided by 2, the other side of the equation. If you want to find the inverse algebraically, which is what we just did, okay, to find the inverse algebraically, Find the inverse algebraically, which just means take its equation, find another equation for the inverse. If you want, what we did first was we switched x and y. Switch x and y, and then we solved for y. Now, the solving for y part, if you think about it, this is the inverse even before you solve for y. Once you switch x and y, this is its inverse. This thing right here is the inverse of this. It's just the convention to solve for y to write it as a function. All right, now let's look at the graph. We've looked at the table of the two, big messy table that I made, and we've looked at the equation. Okay, table has the coordinates switched. Equation has the variables switched. What does a graph have? We're going to graph those two functions right now. If we were to put these two functions in here, let's put the original one in first, which is 2x minus 3. And there it is. There's that line. Okay, it's a line of what you expect. Y-intercept of -3, slope of 2. Now we're going to put the other one in here. Now we can put it in a couple different ways. We can put it in this way, 2y minus 3. Just the way we said. You can put it in here before you've isolated y. That's its inverse. That blue line there is the inverse of this line. The points that kind of correspond to each other, just the way in the table, let's say we have this point right here, 0, -3. The point that corresponds on its inverse, on the blue line, has those two coordinates reversed. 0, -3 has been changed to this point right here, which is -3, 0. Those coordinates have switched. This point here, whatever this, I can't quite get it, but it's 1.50. There we go. That point's become, instead of 1.50, it's become 0, 1.5. I don't know if it's going to stop in the right place. A little touchy. 0, 1.5. Coordinates are interchanged. Now there is one point here, up here, that doesn't change when you graph the inverse. This point right here, 3, 3, doesn't change. If you look at its coordinates, you can figure out why it doesn't change. The coordinates are 3, 3. The x and the y are the same. So when you interchange them, they're still the same. They don't change. 3, 3 becomes 3, 3. Any point that has the same coordinates doesn't change. If the x and the y are the same, when you interchange them, it doesn't matter. Now you think about on here where that's true, where y is equal to x. Where y is equal to x, it doesn't change. Now I'm actually going to graph a line here for you. I'm going to graph the line y equals x to show you. Let's pick a different color so we can keep it all straight here. That line down the middle, that represents the line of symmetry for these two things. This is actually, these two lines are related by this y equals x line. These two lines are actually, it's maybe hard to see, but these two lines are reflections of each other across that green line. If you imagine the green line is a mirror, these are actually reflections. Finding the inverse graphically is actually the same as reflecting it across this line, y equals x. And again, the reason is because those are the points that don't change. Anywhere along that line, anywhere I go here on this line, coordinates are the same, right? Y equals x, it's called y equals x because the coordinates are the same. Anywhere you go along that line, coordinates are the same. Let's look at some other equations here. If we're going to draw this, we're going to draw the inverse of this. We can do it just by creating this this graph, just by doing exactly what we saw happen there. Let's make that a bit smaller so we can fit it in the screen. If we're gonna create the inverse of this thing. We're gonna create it by just looking at the coordinates. If we see this point right here, that point is 0, 4. That point should go to right here, 4, 0. Okay, that point's gone to there. This point down here, let's just track a few of the points here. This point is 3, -5. So where is it going to go? It's going to go to -5, -5, 3. It's going to go to right there. -5, 3. because you've switched those coordinates. And then the third one here, let's go to this one right up here. That's 4, 2. That's going to go to 2, 4 right there. All right. Now, we can connect up all those points. Actually, now what have I done wrong? Oh, I'm having a hard time seeing my negatives here. 4, negative 2. It looked like it was going to be a bit weird. That's 4, negative 2, so it's going to become negative 2, 4. That looks a lot better. Negative 2, 4. All right, so that's where those 3 points have gone. We've switched them around. If you're now going to graph that, if we want to draw the graph of that, we connect up those points and just confirm that it looks the way we want it to look. That, lost my one dot there, but that's okay. It looks more or less the same other than my coordinates there. Now that's what you expect it to be, which is that mirror image across this line here. I'm going to draw this line for you. That line y equals x down the middle. And you'll see that it's, okay, that line more or less right there. A little bit crooked at the top, but you get the idea. It's a reflection across that line. All right? That's how you draw the inverse graphically. Create the inverse by reflecting it across this line, y equals x. Now, what about a slightly more complicated function there, like f of x equals x squared minus 4. This is obviously a parabola with the squared in it. If you're finding that inverse of that thing, we can find it exactly how we did it before. We can say if this function is y equals x squared minus 4. Let's go to the graph first and see what it looks like. You probably predict what it looks like, but we're going to have x squared minus 4. X squared minus 4. Okay, that's what that graph looks like. Now, to find the inverse of this thing, we can, we'll do it graphically first. Let's put it graphically. If we just change it to x equals y squared minus 4, you're going to get that inverse the way you expected there. And we can add our line y equals x in there to see the reflection. Stick with the colors we had it before. All right, that's a reflection across that line, y equals x. Okay, that's the line of symmetry between those two things. Now, something to notice here, though, is the original thing is a function. The original orange curve. Y equals x squared minus 4 is a function. Any x value only has one y value. It passes the vertical line test. The blue one, however, its inverse is not a function. Not a function. Okay, the blue one doesn't pass the vertical line test because it's got two y values here. Say for 5 has a plus 3 and a minus 3. There's two y values for almost every x value here, other than at the vertex. That one's not a function. If you want to, you can tell from you've heard of the vertical line test to test whether something's a function. You could actually use a horizontal line test on this function to tell whether its inverse is going to be a function. If all you had is this, and you were asked, is its inverse going to be a function? The fact that it curves back up like this, it fails to, if you imagine a horizontal line here, it's going to touch it twice, means its inverse is not going to be a function. Now, let's find this algebraically and see if we can confirm this, what's going on here. All right, so if we start with that, we're going to find it algebraically by switching the x and the y. So we're going to make it x equals y squared minus 4. If we want to isolate the y here, we have to move that 4 over. X minus 4 is y squared. But now what you have to do is take the square root of both sides, because that's the inverse of that squaring operation. Now the problem is when you square root both sides, when you had this squared before, it could have been a positive or negative value you had here as compared to the other side. When you square root it, then you need to have on one side or the other a plus or minus just to account for the fact that they could have been opposites instead of the same number. So what you actually have here is you have y equals plus or minus square root of x minus 4. That plus or minus you're going to find actually is why it's not a function, right? If we have y equals plus or minus square root of x minus 4, if you made a quick little table of values here, if you chose a number like, let's pick something like 8. Pick easy things here, right? Let's pick 5 first. If we pick 5 there, you put a 5 in there, 5 minus 4, right? Plus or minus square root of 5 minus 4. This is plus or minus square root of 1. This is plus or minus 1. You have two values in here, plus or minus 1. It's not a function because you got two y values for one x value. You're going to find that if you try 8, you get plus or minus 2. If you try values above that as well, you're going to get two y values. It's not a function. That doesn't matter. It's still its inverse. This is the inverse of this, or you can write it this way. This is the inverse of that. Now the question though is, can you do something to it so that it is a function? How could you restrict that original thing so that its inverse is a function? If we look at this, is there some way we could restrict this so that its inverse is a function? For its inverse to be a function, we only want the top half or the bottom half. Okay, we need the top half or the bottom half. We can't have both halves. Actually, if you put it in the way we had it on the other side there, y equals, let's find our buttons here. Where is it? I think I had it. Square root of x plus 4. If you just put in the square root there, you get the top half. If you put in the negative, you get the bottom half. All right, one half or the other. The problem is the way this one's written, you get both halves. If we want to restrict it so that so we just get that top half, we want to restrict this so we just have this half the parabola. The way you're going to do that is say, how about we graph this parabola where x is greater than 0. Now in this program, the way that you put in restrictions is you have to put them beforehand. So you have to say where x is greater than 0, like that, except I just hit the wrong thing. X is greater than 0, like that, and then you have just that half of it. All right. If you restrict that original function to say x is greater than 0, its inverse is a function. Or let's say you were looking to make it to find just that. Well, you could have restricted it the other way. You could have said, I don't want that side of it. I want the other side of it. So I could say I want to make it where x is less than 0, and then I get the other half that parabola. That works as well, right? If you restrict it to half the original parabola, then you get the inverse of being a function. This is a function. All right? So we have the inverse 3 different ways. We have the inverse when we look at it algebraically from an equation. Switch x and y, and then solve for y if you want to write it as a function. We have the inverse from a graph. You reflect over the line y equals x, and from points or a table, right, coordinates, reverse the coordinates, right? Switch x and y, same thing. Reverse coordinates. It's exactly the same thing. That's what the inverse is, right? One function that undoes the other one. If one's called f, the other one's called f inverse, which you use a little -1 like that, right? And that's inverse functions.